Dr. Bob Bartlett. In this session, entitled Physiology, we will look at the effects of the physical gas laws as they apply to physiology. Specific topics that we will examine include the oxygen cascade. We'll also look at carbon dioxide transport and why that's important in the practice. We'll also look at cardiac effects that hyperbaric therapy has, and we'll also examine the metabolic effects. Then we will take all of these and weave them into an understanding of the mechanisms of action. And following that, we will look at least at the broad indications for what exactly hyperbaric therapy is used for. Now, in this introductory session on the clinical indications, we will simply look at the general applications, and then we will look in greater detail through each of the modules, such as radiation injury, diabetic ulcers, and osteomyelitis. Now, beginning here with this concept of the oxygen cascade. From that very first breath out here in the atmosphere, we are inspiring a partial pressure of oxygen of about 159 millimeters of mercury. Now, in the physics section, we looked at Dalton's law. And here is the application of Dalton's law, the law of partial pressures. Our atmosphere is a mixture of gases, nitrogen, oxygen. And we know that 21% is oxygen. So at sea level pressure, one is typically inspiring about 159 millimeters. But you'll notice that there can also be an effect of barometric pressure. So here's a question that I oftentimes ask people. What is the partial pressure of oxygen at the top of Mount Everest? Or let's rephrase that question, what is the percent of oxygen at the top of Mount Everest? Well, the percent of oxygen is 21%. Why? Well, it's still air. We're still on planet Earth. However, some of you would recognize that the partial pressure of oxygen is extremely low. And that is why mountaineers oftentimes have to take supplemental oxygen because of the enormous height of the altitude or the barometric pressure. So as we start off here at 159 millimeters, assuming we're at sea level, we take into consideration the inspired percentage of oxygen, which under normal conditions is 21%, or we could be breathing 100%, and then we factor in the consideration of barometric pressure. The air moves to the lungs. The purpose of the lungs, of course, is to oxygenate the bloodstream. So here we consider the alveolar PO2. Now, the alveolar PO2 is a function of both alveolar ventilation, that is the number of breaths we're taking per minute, and the oxygen consumption. We then consider the interface of the alveolus with the bloodstream itself. And the arterial PO2 is a function of two major factors. The first of which is the VQ ratio, or ventilation perfusion ratio, and then there's a factor of venous admixture. Now, the lung as an organ is responsible for oxygenation, and many people will liken it to a very large sponge. If you consider a wet sponge, at the bottom of the sponge, it's very heavy and the cells are compressed, and the same is true of our lungs. The top of the lung is very light by comparison. So the lung is not a perfect organ. That is to say that at the bottom we may find that the lung is actually overperfused compared to the top of the lung. In contrast, the top of the lung oftentimes overventilates. Pulmonary physiologists will refer to this as West zones 1, 2, and 3. But the point is that when we consider the scatter of VQ ratios, the minor imperfections that characterizes the lungs, and the fact that some patients may have shunts or venous admixture, blood that bypasses the lungs, the net effect is we end up with an arterial PO2 that's about 100 millimeters. Now, from the arterial PO2, we move to the periphery, and here the actual amount of oxygen that arrives at the cell is a function of blood flow, hemoglobin concentration, and of course PO2. At the cellular level, the PO2 is only about 8 millimeters. Now I want you to pause for just a moment and examine the slide. We start off in the atmosphere with an enormous pressure, 159 millimeters. And this pressure drops all the way down to 8 millimeters. 8 millimeters is the actual working pressure at the cellular level where oxygen combines with hydroxyprolase or mitochondria to either produce collagen or power the cell. And you can see here the enormous reduction in pressure. You know, a common question that I'm typically asked is, do we need hyperbaric therapy to help heal wounds? Could we not achieve the same benefits utilizing just oxygen by mask? Well, if you look at the enormous reduction in pressure from 159 millimeters down to 8, it's going to take an enormous amount of change on the top line to affect the bottom line. Let's look more closely at alveolar PO2. You know, the alveolar gas equation is a common concept taught in physiology courses worldwide. Here is the alveolar gas equation. The factors that one considers in this equation would be the following. We see the notation PATA, which is the pressure of the gas expressed in atmospheres absolute, minus water vapor, and of course water vapor is also a gas. And again, in accordance with Dalton's law, we need to take that into consideration. Anybody who's exhaled on a cold winter's day and seen that puff of smoke knows that we do have a lot of water vapor in the lungs. Times FiO2, which is a fraction of inspired percent of oxygen. Looking here at our alveolar gas equation, the FiO2, of course, would be around 0.21. Then we have that final term, 40/RQ. So what's that all about? Well, RQ is respiratory quotient. And what we're referring to here is the amount of carbon dioxide that each of us is producing. After all, the endpoint of metabolism is the production of carbon dioxide. Another important function of the lung is to exhaust this carbon dioxide back out into the atmosphere. So let's start to plug some of these concepts in using real numbers. Under normal room air conditions, we're operating at sea level at 760 millimeters, minus water vapor pressure, 47 millimeters, times the fraction inspired percent of oxygen, which at sea level would be 0.21, minus 40 over 0.8. Now that respiratory quotient of 0.8 is a function of your diet. You know, your parents were right when they said you are what you eat. So if you're on something like the Atkins diet, high in protein, you don't produce a lot of carbon dioxide. If you're like me, on the Dunkin' Donuts diet, rich in carbohydrates, you produce a lot of carbon dioxide. But for most people with a typical diet, it's 0.8. So moving along here in our equation, we see that under normal conditions, we are producing an alveolar PO2 of about 100 millimeters. And this is just about right. After all, an arterial blood gas is also about 100 millimeters. Now let's examine what happens under hyperbaric conditions. Under hyperbaric conditions, we will have an enormous change in the atmospheric pressure. However, water vapor will be unaffected. Now, the FiO2 under these conditions is 1. You know, there are only a few times in medicine where one has truly 100% oxygen. One is for the patient who is intubated, and the other is for somebody who is actually encased in a chamber with pure oxygen. Now, as to the amount of carbon dioxide, that will be unchanged. Whatever you ate for breakfast that morning is still going on in the chamber. So let's look at this equation as we start to put in the numbers. Let's say in this example that the patient is at 3 atmospheres absolute. That would be 2,280 millimeters minus water vapor times 1, a perfect unity here, pure oxygen, minus your carbon dioxide. As you distill the numbers down, you find that the alveolar PO2 is now 2,183 millimeters. This is almost a 20-fold increase compared to what we just saw a moment ago under normal conditions. Now, there are a number of other considerations in terms of how much oxygen we're going to transport. For example, the amount of hemoglobin in your bloodstream will also govern the amount of oxygen in the blood. The normal solubility of oxygen in hemoglobin is 1.34 mLs of oxygen per gram of hemoglobin. Now, whose law is that? Well, that's Henry's law, the solubility of a gas in a liquid. So I'm going to periodically reinforce some of the other principles we've talked about elsewhere in training. Under normal conditions, you and I are typically at about 100% saturation. Any of you who have put a pulse ox on your finger, you probably noticed it's typically 99 or 100%. Now, the arterial content of oxygen for a normal patient with 15 grams of hemoglobin is about 20 volumes percent. After the red cell has made its way through the body to the venous side, the volume percent of oxygen is typically 14%. So this makes a difference of 6 volumes percent. Let me pause here for just a moment, though, to talk about this concept of volumes percent, just in case you're not familiar with this. Volume percent is a very common concept in chemistry. And what volume percent means is that if I have 100 cc's of liquid, and in this case 20 volumes percent means that in the 100 cc's of liquid I have 20 cc's of oxygen. If any of you have been shopping in a grocery store and you're an informed consumer and you look at the side of a can of beer, it oftentimes talks about alcohol in volumes percent. So if it says alcohol 5 volumes percent, what they mean is that if you have 100 cc's of alcohol, 100 cc's of beer, you have 5 cc's of alcohol. If you have 100 ounces of beer, you have 5 ounces of alcohol. Or if you prefer, if you are at a fraternity and you have 100 gallons of beer, you've got 5 gallons of alcohol. So that's what the concept of volume percent means. Going back to our slide, you might notice 6 volumes percent is the typical extraction of oxygen. And if you're a person like Borma, who is trying to predict, can you exist in the virtual absence of blood, this number, 6 volumes percent, becomes extremely important. We'll come back to this here in just a moment. The other consideration is the amount of oxygen dissolved in the plasma. Now, the solubility of oxygen in plasma is extremely low, 0.003 mLs per 100 cc's per millimeter of mercury. However, under hyperbaric conditions, we are working with very high pressures. So let's look at what happens in terms of the amount of oxygen we can dissolve in the plasma under hyperbaric conditions. At 1 ATA, we would have 2.1 volumes percent of oxygen dissolved. At 2 ATA, it's 4.2 volumes percent, and at 3, it's 6.3 volumes percent. So there you have it. We are actually meeting the metabolic demands to support life without blood. And this is precisely what Borma did when he sat down on paper to calculate, is it possible? And the math certainly said that it was. And then all that was required is that he put the physiology to the test to demonstrate that in fact it was achievable. Now, the next gas that I'd like to examine in this session is carbon dioxide transport. Carbon dioxide, of course, is the byproduct of metabolism, and the other important role of the lung is to exhaust this gas to the atmosphere. The transport of carbon dioxide is really a miraculous phenomenon, because the way that we move carbon dioxide back to the lungs is by 3 principal pathways. 75% is moved in the form of bicarb, a solid. 20% is transported as carbamine, a hemoglobin. Now, in studying red cell physiology, most of us tend to focus on oxygen. And we sometimes forget the fact that when the red cell releases oxygen, it also does something that's equally important. It will pick up carbon dioxide in its place. So the red cell becomes a very important shuttle to move carbon dioxide back to the lungs. The final transport of carbon dioxide is in a physically dissolved form. So, when you're measuring arterial blood gas and you're peering down at that typical number for PCO2 of 40 millimeters, what you need to understand is that it's really only the tip of the iceberg. The vast majority of carbon dioxide coming back to the lungs is really coming in a solid state form, such as bicarbonate. Now, the movement of this gas as a solid is truly an example of some brilliant physiology. Consider for a moment what would occur if almost all the carbon dioxide came back to the lungs as a gas. Anybody who's taken a bottle of Coke and shaken it up realizes the explosive force of the gas coming out of that solution. Well, what do you suppose would happen to a human being if they were jumping on a trampoline, or a gymnast doing a triple dismount, and they hit the floor and all this gas bubbled out of their system? So nature has really been very eloquent here in converting carbon dioxide, the gas, into bicarb, the solid. Now, what makes this possible is an enzyme called carbonic anhydrase. Carbonic anhydrase is a very powerful catalyst that allows CO2, the gas, to convert into CO2, the solid. But this second pathway, the carbaminohemoglobin, is one that deserves additional attention. As we transport the red cell out to the periphery, under normal conditions, it typically does not deoxygenate. Now, if we examine the red cell as it begins its journey in the aorta, under hyperbaric conditions, 2,000 millimeters of oxygen, of course the red cell is 100% saturated. What do you suppose is the red cell's saturation when it returns to the heart? Well, it's actually 100%. Now you may say, well, how can that be? How do we deliver the oxygen? Well, consider we start at 2,000 millimeters of mercury. As we are going down through the blood vessels delivering this oxygen, the gas pressure is dropping very quickly. 2,000, 1,900, 1812, 1,000, 876. This thing is dropping like a bad stock pick. However, when we reach the venous side, the partial pressure of oxygen is still about 200 millimeters. So what is the percent saturation of a red cell? Well, of course, it's still 100%. So the important point here is that the red cell is no longer contributing to the transport of carbon dioxide. So coming back to our slide here, the concern is that under hyperbaric conditions, we may possibly impair the delivery of carbon dioxide back to the lungs. And for those of you taking care of patients with chronic wounds, many of whom are elderly, some of whom certainly have chronic lung disease, this raises a theoretical concern that PCO2 or carbon dioxide retention might occur. However, clinically, we do not observe this to be a problem. Why? Well, the carbonic anhydrase pathway has so much power, so much capacity, that even when we lose this one transport mechanism, that is to say the carbaminohemoglobin, the carbonic anhydrase pathway has more than enough capacity to pick up the slack and ensure that we do not have a problem. Plus, if you draw on other clinical insights, this should also be apparent. For example, consider a patient with sickle cell anemia. They typically live with a hemoglobin of only 5 or 6 grams, and we certainly don't worry that they have problems with CO2 retention. Some of you have seen patients with extreme anemia. You have concerns, but they're certainly not that you're going to put them on the ventilator. So again, this really is a clinical demonstration that the carbonic anhydrase serves a very important role in moving CO2 out of the system.